Hi, and welcome back to Econometrics B. So today it's about corner solution responses, and we also will talk a little bit about sensor regression models, okay? Because these models that we are using to model these two phenomena are actually quite similar. Okay? So basically, both of these models, both corner solution outcome models and sensor regression models, are used to explain some of the same phenomena. A continuous, if you're interested in modeling a continuous random variable with a probability mass at a certain point, okay, or certain points, it could be more places. Okay. Now, when would that happen? Well, that could happen in these two cases that we will look at that are fundamentally different, um, but have some similarities in the way we are modeling. So one case is data censoring, and the classic example here is top coding of wealth. So it may be that you observe the entire distribution of wealth, but actually not the entire distribution, because at some threshold levels, say, everybody who earns more than 10 million kroner, you would not, who owns more than 10 million kroner, you would not observe what the actual wealth was, but just that they had more than 10 million kroner. Okay. Or whatever currency you're working with. Okay. So that's clearly a data recording issue. It's not about that the people who are censored, have that wealth, right? They have a higher wealth. You just don't know what it is. That is also the reason why it's in chapter 19, I guess, because it's a data related issue, and it's about some kind of sample selection and censoring. Okay, so Woolridge decided to put that into that chapter. I'm going to treat it here because it's very similar to the other case in terms of the observed outcomes, or namely corner solution outcomes. Here we can also have mass points. Okay, so for one example would be, say, demand of a good. Okay, you can't demand a negative amount of many goods. So there'll be a mass point. There'll be lots of people who would have a demand of zero, and who doesn't buy the good at all. But for those people who buys the good, well, there could be like a continuum demand, because people are different. There'll be, changes in prices and income and so on, that make people demand different amounts. Okay. Now, the difference here is quite fundamental. It is that the corner solution outcome model, well, you have a mass point in both cases, but in the corner solution outcome model, it's not because of a data recording issue. It's because of the behavior of the agent. It's because the agent says, "Oh, I would really like not to sell these goods, but I don't want, definitely don't want to buy them. It's not really in my preference relation in any way. So I have just a continue. I just have a demand of zero." Okay, so this is about the behavior of the agent. He is in a corner solution where it just finds it's not optimal to buy any amount of that good. Okay. Well, that appears in micro, right? So we're going to have it here as well in econometrics. The reason why these are treated together is because they're often modeled with the Tobit model, which is the main topic of today. This is kind of related a little bit also to a topic in the chapter on sample selection, where that's called incidental truncation. Okay, so one example here would be, we're interested in modeling the earnings for self-employed, where profits is only observed for the people who are self-employed. Okay. Now, the difference to the case that we're looking at today is that, for example, with the demand, it would be obvious that if you have a recording of zero, it is actually a demand of zero. But for a self-employed, or for an individual who's not self-employed, where you don't have that profit observed, it's not because those profits would have been zero had they been self-employed. So this is a little bit different. So loosely speaking, you can see they appear very similar type in terms of this truncation, but here in sample selection case, sample selection case with the self-employed, we would not observe the truncated value. We'll entirely lose that observation. Okay. Anyway, we'll talk about that later, but it's just good to try to get an overview of how what are the different types of models. You need to pick the right one for your application, right? Okay, so here's the example with top coding of wealth. So And let's just get a little bit of a notation introduced. So we have this latent variable y star, and let's assume that as well. Okay, we want to write up a regression model for y star, so explain how that is affected by some explanatory variable x, for example. We haven't brought them in yet, but they're going to come. Now the problem is that y star is not what we observe. We observe really the minimum of y star and a. Okay, and a, that's the truncation point. Okay, now this is the underlying distribution of wealth, the real wealth, that had we observed it perfectly. But what we will observe is this distribution, and then there's mass point here. All that mass here has been put together out here in this particular point. Okay, so we have a mass, and say here y is really centered because the data recording mechanism, not because of behavior. So that's the textbook example of that. Okay, and there are many variables that are exactly like that. Okay, where you for some reason have either interval coded data, or you have you're making some censoring because of the way you've collected the data. Okay, so here's another example. That's demand. Okay, you got your here you got the good of interest, and then there may be some other goods. Okay, and you got your budget set here, and then it's we need to find the optimal demand. Well, that's where the indifference curve here. These are different indifference curves for different individuals or at different prices, and then or for different individuals. And then we will find that optimal demand where this tangent to the indifference curve, the budget line. So that's your micro 101. So we know how to do that. But then in data, not everybody have the same prices and preferences and income and so on. And so this budget line, that's gonna change with income and prices, and the preferences, they would shoot up and down these different indifference curves, and you're gonna have like a lot of heterogeneity in demand. Okay, so different people, they're gonna demand different amounts of good. Okay, but see, you can not in this example demand less than 0. Okay, so there'll be a corner solution outcome up here where you cannot find like a basically a tangent line anymore. So the first order conditions for the consumer's prop is not sufficient. So we end up in the corner solution. Okay, and they're actually going to be, if you have like a smooth distribution of preferences or some variation in prices, you're going to have actually a mass point where a lot of people with different preferences are all going to have demand equal to 0. Okay, and that's, well, it's not really that clear here, but I was trying to illustrate that there was like a mass point here. Okay, so there's supposed to be a mass point, probably mass at y equal to 0. Okay, and then there's going to be like a smooth distribution that's a rise from various combinations of income and prices and preferences for the people who are actually demanding a positive amount of that good. So you get like a continuous distribution with a mass probability of 0. Okay, so that's like the structural interpretation of this demand example, and why you could observe a positive probability mass at one point, whereas you have like a continuous distribution throughout the rest of the distribution. And of course, there's no negative, right? So there's no mass out here. So there's many of the examples like this, and the textbook examples of corner solution outcome cases, that'll be like demand or consumption that need to be positive. Hours worked, well, that's a supply, right? Hours worked, that must be positive, right? So some people there's a mass point at 0 because some people are on the couch, right, or doing something else, not at the labor market. This house evaluations must be positive, right? Firm exports, or this may be a fixed quota of exporting. So the amount that you export is 0 for many firms. Okay? So there's so many examples, like charitable contributions. That's another example of something that cannot be negative. Why some people might actually prefer it. They're not going to get money out of Red Cross by calling them and say, I want a negative demand of your product. Okay. That's not how it works with charity. So these are examples where there can be lots of people who are actually demanding zero or having zero at some point, or the mass point that probably at zero. But it doesn't have to be at zero. It can be at other places. Okay. So an example from my own research is taxation of the self-employed. And see here, the tax system is piecewise linear, and there's going to be a kink in the budget set for taxpayers. For example, at the middle and the top tax thresholds. We don't have the middle taxes anymore, but then at least at the top tax threshold. Okay, and then that means if you look at this figure here, then suddenly there's going to be a kink. If you start to like work more, well, you supply more hours, well, there's going to be a kink, because suddenly your after tax wage is going to fall, which means that the prices are changing as you change this variable. Okay, and this means that you can see, again, you can have like a whole continuum of consumers that will be collected at that point, or because that there'll be like several points will be in that corner solution where the kink is. Okay, that creates something called bunching. Okay, or a probability mass point around that kink. Okay, and so we should expect to see mass points on these kinks. And so here's some examples. Okay, here's the distribution of personal income for this is for workers, and this is for the self-employed. Okay, and you can see how the marginal tax is changing throughout the distribution, corresponding to a kink in the budget set. Okay, now so you would expect to see a little bit of bunching around here. There's not that much bunching for the wage workers, and there's good reasons for it, right? Because there's a bunch of other things that's really hard to adjust. Maybe if you on the intensive margin, if you're changing your labor supply just a little bit, well, then it's not, you can call the boss and say, no, sorry, I'm not coming to work for the rest of the year. I'm only going to start next year, where I'm back on the below the top tax, right? But self-employed, they have much better possibilities of moving around income from year to year and declaring income and so on, right? So if you look at their reported taxable income or personal income, that's really massive mass points at those kinks of the distribution. Okay, so here's an example where the mass point at the top tax cutoff is 4.3%. Okay, so it's like these are people that declare their income on the top tax threshold plus minus something like 500 kroner. It's 5% of the self-employed. So that's or 4 point. I'm getting blind. I can't see. The font is too small. Why don't we zoom in? It's 4.29 at that cutoff. Okay, so so that's a lot of mass, right? Then it's about how you interpret what that really means. It turns out for the self-employed, it's not because they suddenly stop working on close down the shop. It's because they can move their income from year to year, and then they end in this corner solution. Often actually many years in a row, because they could just move the income for next year or have other ways of deducting their income. And so they stay on the top tax threshold for several years. Well, so that you can read all about that in the paper. There's a link to it down here in this paper that I wrote with a colleague, Daniel Lemire. But the bottom line is you see mass points, okay, in the distribution of continuous distribution of random variables of interest. Okay, you might want to model what is the personal income of the labor supply for measured in terms of how much profits the self-employed earned, and explain that as a function of a bunch of explanatory variables. But then you need to take into account those mass points that exist in that distribution. Okay, so here you have this bunching at or mass point at the top tax threshold, and you can use some kind of corner solution outcome model. Well, you'll not really just use the Tobit model I'm going to show you straight up. You have to like modify it a little bit, but the idea is the same. That's a mass point. Okay? And actually, the way you start estimating responses to taxation today is by utilizing the information that there is in this mass point. Okay, it's something called the bunching method by Emmanuel Saris, that's become very popular. Anyway, that's really outside the curriculum. So let's not talk about that. We need to do a little bit of Python. So I'm going to read in some libraries. We need the basically, we need NumPy and a random number generator, and then we need some plotting. And then I've collected a bunch of functions in this library that's called Tobit. So I'm going to read that in. And that's available right over here. You see that that there's a bunch of different functions for simulating the data. You got your objective function. That's a function for the scores, and then there's the main function Tobit you can call if you have explanatory variables and independent variables, and then a bunch of other functions. Okay, so we'll get to it. Okay, so why don't we just read that stuff in and then move on. So I want to show you now like just a little bit of an example here with some simulated data, and show you what are the observed frequencies in this particular case. So what we do is we read in the data, we simulate data from the Tobit model, and I'll explain it later, and then we basically plot some data, and this is the type of data that you would then have, right? So you have, again, you have your probability mass point distribute, the mass point here, and then the continuum, continuous distribution here, and your observed data here, you would have on the axis, you would have y, and then you have, say, some explanatory variable, and clearly see here there's some kind of linear relationship going on for all the positive values, but then there's a bunch of values that are just essentially censored to 0. And by the way, the wealth example can be also, I mean, we were talking about the minimum there. It could be, they could also, we could rephrase this model completely so that it captured that as well. Anyway, what you see is you observe a bunch of observations that are all 0. These are those up here, and then a distribution of a continuous distribution of the explanatory of the dependent variable y. And this is so here we have plotted y against one explanatory variable x. Okay, and so how do we actually come up with a model? I mean, here it looks actually fairly linear in this area here, and that's actually also what it's generated to be. But then it would suddenly start to bend off here, right? So what's going on? Anyway, so we'll move on to the Tobit model for to model these kind of behavior. And here's a Tobit model. It's kind of originally, way back introduced by James Tobin. And the idea is that there's an underlying latent variable. Okay, our latent variable is called y star. Okay, and that's xi beta plus epsilon, and epsilon is normally distributed. And if you were to observe y star, well, you just do a linear regression of y star and x, and you'll estimate beta. But then the problem is the y star is not really observed. So you think about the top coding of wealth example, we observe basically not y star, but the minimum of y star in some and some top cutoff. Or it could be in the other way, that like in the bottom there was a truncation or some other point. Okay. Now, what we're going to assume here, we're going to formulate a model where the observational rule is the following. So y, that's what we observed, that's equal to basically 0 if y star is negative, and otherwise you would observe y star. Okay, so I mean, this is completely equivalent to just write it like this. Okay, so yi is the maximum of 0 and y star, and of course here 0. That doesn't have to be 0. You can essentially put in a truncation point wherever you want, or you can revise this so it becomes the minimum instead, and then the model would be slightly different, and then it could accommodate the wealth example as well. Okay, so but we're going to work with this. This is like the standard formulation of the Tobit model. And by the way, this is also the model that generated the data. Okay, so now let's see if we can look at those data. Okay, so essentially we created some data from this model, and you can go in and look at it yourself. That is in sim data. I'm not gonna dwell too much with it, but it's right here. And what you see here is we essentially have a linear model that's saying this y star is x beta plus u. and then you can have different distributions of U. I'm going to talk about that later, but really this is our Y star, and then the observed value of Y, well, that's the maximum of that at 0. Okay, so plainly simple, the same as we got over here, this observational rule, and then you got your Y star formulated linear index. Okay, so relatively simple model. So we're gonna move on, and then you might ask, why? What if we just, why wouldn't you just? We don't observe Y star, but what would happen if we just didn't care and try to estimate on, say, the truncated observations? Okay, so or say all the observations, including the zeros. Okay, would you actually get the right answer? Okay, and so here's what you get if you basically estimate only using the positive observations, so these observations that are up here, and this is what you get if you also include the censored observations, though that were 0. And then the question is, which one should I pick, and is it even measuring what I'm interested in? So say the partial effect of changing X on Y star, if I'm in the censoring case, or maybe a more complicated object in the corner solution outcome case, okay, where we want to understand the underlying mechanism in the economic model. So I'm going to try now to see, okay, now you can't do that in reality, but I'm going to assume I know Y star because I'm God and I created the data. Okay, so at least well, sorry about that. Probably not appropriate to say you're God, but at least I'm the data generator. Okay, so so here's I'm adding really into this plot. I'm adding all the censored values. Okay, so that is what would happen had I observed Y star, or the underlying value Y star, and regress that on the explanatory variable X. Okay, and again, sorry about the not being clear with the labels. We got Y here and you got X here, or Y star if you also have these. Okay, so that's basically that's a line, and you can see it's kind of going through, and I can tell you the slope of this line. Well, that's equal to the beta that was used to generate the model. So that slope is supposed to be 1, because that's what we assumed here. Okay. And then you can, of course, you can play around with parameters. Say if I increase beta to 1, well, this means that now we kind of we add more to the constant here, so that increases the average value of Y and move it more away from the truncation point. And now you can see these lines are suddenly moving closer together. Or even if you put it equal to 10, well, you won't have any censoring issue, and all these things, all these different regression line would just completely overlap. Okay, so that's basically the idea. But we are unfortunately in the situation where we have the censoring case. Okay, so okay, so sorry, yeah. Oh, we just need to. This is the case we're looking at. Okay, so where we potentially have censoring, and we cannot just regress Y for the observed value on X, or Y for of the censored or truncated values of Y on X for those individuals that are censored. So that's not doable. So you may actually need to impose more structure. It turns out that OLS is not doing it for it, so we want to estimate the model. In this case, we think that the Tobit model would be appropriate. And so here is our attempt to derive the likelihood. Okay, and I'm going to take a short break, and then we'll talk about maximum likelihood estimation of the Tobit model in just a second.